Hello ladies and gentlemen, my name is Christian Kaiser. I'm scientist in the Department Inorganic Materials and Recycling at the Fraunhofer Institute for Building Physics IBB in Germany. There research and develop cement-free building materials. Today we will look at a new type of building materials, geopolymers. Geopolymers can be used to produce building materials that are similar in form and application to concrete. However, no cement is required for their production. In this module, we will take a closer look at the advantages this brings. Let's start. Why are we involved in the development of cement-free building materials at all? A high proportion of building materials are currently made from cement. As this diagram shows, cement production accounts for about 90% of global industrial CO2 emissions. Cement has to be burned at very high temperature, about 1000 degrees and higher Celsius. These high temperatures require a great deal of energy to produce and therefore also results in high CO2 emissions. Here you can see the total CO2 emissions worldwide. In 2019, just over 36 billion tons of CO2 were emitted. By 2050, this is expected to rise to about 34 billion tons per year if we continue to build as we do now. Worldwide, almost 15 billion tons of CO2 are emitted by industry alone. The production of cement accounts for almost 3 billion tons of this. In Germany alone, cement production releases around 20 million tons of CO2 per year. If we continue to build in the same way as before, we will emit twice as much CO2 in construction sector alone by 2015. As we are still expected to release globally in order to achieve the 1.5 degree target. So as you can see, we urgently need to work on developing more climate-friendly building materials. Replacing cement-bound building materials with cement-free building materials offers us great advantages here. Material based on geopolymers offer high potential here. The picture shows geopolymer specimen that is very similar to concrete in terms of the structure and capabilities. However, it is a cement-free building material. Geopolymers, also called alkali-activated binders, are cement-free and have higher strength values than concrete. Unlike cementitious building materials, their basis materials does not be heated so high. It only needs to be heated at few hundred degrees Celsius. They therefore require significantly less energy to produce and therefore have a better ecological balance. They generally have very high strength and also resistant to moisture and acids. Because of their very good freeze-thaw stability, they are already being used in some places for the construction of, for example, runways. In addition, they can be produced at very low cost, and for the production, industrial byproducts such as ashes, slags or dust, among others, can be processed, which in turn counteracts the scarcity of gravel or sand resources. We conduct research of various geopolymer materials and can carry out all steps in the production process in our construction materials laboratory, from formulation and mixture, mineralization, optimization to the determination of mechanical properties. Here you can see the individual components that can be used in the production of geopolymers. Various raw materials can be used for production, both primary raw materials and also residual materials such as ashes or slags from waste incineration. So possible raw materials for the use are calcinated clay, fillers, sand and gravel. In addition, an alkali solution, for example water glass, an alkalinous silicate solution and water is needed for the production. The ingredients are now mixed together in a defined ratio in the laboratory. The mixing process is basically identical to that for cementitious building materials. However, with the addition of water glass to geopolymers, one must be more careful as this is a high caustic solution and can quickly change the viscosity. A high proportion of water leads to more porous structures and consequently to lower mechanical strength. As you can see, the result is a viscous mass. This is then poured into a mold. The mass can be then hardened at room temperature, or it can be placed in a warm environment of about 50 to 80 degrees Celsius to speed up the process, the curing process. After the curing, the test specimen can be removed from the mold. You can see, or better, the sound shows how brittle the test specimen is. The high strength and properties are very similar to appearance to concrete. Like building materials made of cement, materials made of geopolymer must be undergoing some material tests. In addition to the mechanical strengths, there are also long-term tests like the freeze-thaw behavior of interest. So, however, in contrast to cementitious building materials, and depending on the country, there exist only few or no standards or testing methods. So this shows that geopolymer are still clearly in development phase, and only a few products have already reached market maturity. So in terms of the microscope image, geopolymer have hardly any crystalline phases. Instead, the geopolymer binary matrix has an amorphous structure such as glass. So geopolymers can be used in different ways, depending on their initial composition. In Australia, geopolymers are used as a material for aircraft runways. In India, entire houses are built from geopolymers, and in Formula One, for example, carbon fiber reinforced geopolymers are used for exhaust pipes. Due to their high resistance to acids, future use of geopolymers, for example, in wastewater pipes is also conceivable. So at Fraunhofer IVP, we are mainly working on the use of geopolymers for the construction sector. For example, we want to use novel foaming processes to develop geopolymers from which we can produce non-combustible and cement-free insulating materials. Or another approach, we're using geopolymers as binder for building materials made from renewable raw materials. So the first article about geopolymers was published as early as in the 1970s. So, but the topic of alkaline activated materials has been pursued since the 1950s and before. However, geopolymers have only become the focus of international construction chemicals research in the last, I would say, 12 years. So original geopolymers were produced from metakaolin. Meanwhile, geopolymers can be produced from very different siliceous materials, such as fly ash or granular blast furnace slag, all the way to rice husk ash. So the main scientific challenge is that the formation mechanism for geopolymers is still not exactly clear. Using conventional analytic methods, geopolymers appear as amorphous materials. So that's clear, but the unusual material properties rather suggest nanostructured material with a dense microstructure. Strictly speaking, geopolymers are not polymers at all, as no polymer has ever been detected in material. Analysis, or in summary, a geopolymer is a semi-crystalline amorphous material formed through the polymerization reaction between an aluminum silicate source and an alkaline reagent. In production, geopolymers differ significantly from concrete in the consistency that results when the components are mixed. As you saw earlier, depending on, for example, water content, a tough chewing gum-like mass is formed. Also, the material is high caustic. There is no kind of hydration reaction, and heating shortens the curing time. This makes process a little more complex. In addition, as mentioned earlier, duopolymers have a low carbon footprint and offer the possibility of using residual materials, for example slags, from waste incineration or rice husk ashes. And the use of residual materials bring further environmental benefits compared to the use of primary raw materials. We can thus counteract the scarcity of various raw materials. For example, the shortage of sand, which is becoming more and more widespread worldwide.